Today, we'll be starting our study of exponential and logarithmic functions. An exponential function is a function that can be written this way. F of x equals 2 to the x power. And that 2 could be, well, let's call it a at first. A cannot be 0, nor can it be 1. Okay? The restriction on 0 is, I think, fairly obvious. If we raise 0 to any power, we're still going to get 0. But the same is true for 1. 1 raised to any power is just going to be 1, and just going to give us a straight line. So let's look now at f of x equals 2 to the x. I'm going to start by making a table of values. And as we've done before, I'll start with -3, and go on up to +3. So 2 to the -3 would be +1/8. 2 to the -2 would be 1/4. This would be 1/2. 2 to the 0 power is 1. 2 to the first is 2. And then 4 and 8 complete my table. So to graph this, put y down the middle here. We'll bring x up just 1. So at -3, I'm at +1/8. So 1, 2, 3, and about there. Then I go to +1/4, and then to 1/2, and then to 1. Continuing on, I go to 2, 4, and 8. So when I connect these, I get a nice smooth curve that starts off pretty flat, but very rapidly increases and rises quite steeply. Okay, so exponential functions grow much faster than polynomial functions. Now they ask us a question with this: estimate the height of the graph when x equals 50. So if I had 2 to the 50th power, if each of these is 1 inch, I would have 2 to the 50 divided by 12 inches to the foot, and 5,280 feet to the mile. So when I simplify all that out, when I multiply all this out, I get a number that's approximately 18 billion miles. Pause the video now and work on checkpoint 1. If I were to change this graph, say, let's have g of x equal 3 to the x power. So x and g of x so 3 to the negative 3 power would be 1 over 27. This would be 1 over 9. 1 over 3, 1, 3, 9, and 27. Now I can graph some of that. 1 over 27 would be pretty close to the axis there. 1 over 9, not much more. 1 over 3. Still at 1 here. And then here I'd be at 3. And then at 9. And this last point I can't graph on this scale. I'd have a line like this, a curve like this. So you can see it goes up a little steeper than 2 to the x. And if I were to do some additional graphs, let's say I did h of x equals 10 to the x power. Well, that would start even lower. It still would go through this point, 0, 1, but it would go up even steeper. If I had, let's say k of x was 3 over 2 to the x. So this is still greater than 1, but it is less than 2, which is going to give me a graph that starts off a little bit higher here, but ends up lower here. And what I want you to notice about these graphs is that they all go through this point. This is, whatever the base is to the 0 power, is always going to be 1. And the larger the number is, the more steeply the graph rises on the right side. And all these graphs have some properties in common. All the graphs are above the x-axis. The y-intercept is 1. The graph climbs steeply to the right. The negative x-axis here is a horizontal asymptote. All these powers, all the powers of 3, all the powers of 10, all the powers of 3 over 2, they're all positive numbers, so it will never fall below that x-axis. It's an asymptote. And the larger the base, the more steeply the graph rises. Let's look now at what happens if my exponent is negative. So let's look at g of x equals 2 to the negative x. The negative exponent tells me that I need to flip the base over and make it a fraction. So if I wanted to rewrite this without the negative, I could write it this way. G of x equals 1/2 to the positive x power. And once again, we can make a table of values. And this time when I raise 1/2 to the negative 3 power, I'm taking the reciprocal again, so I'm back to 2, and it's 2 to the third, so 8, 4, no, not 1, 2. And then 1. And then here I'm going to have 1/2. 1/4, and 1/8. So when I graph this, at -3, I'm at 8, and then 4, 2, 1. I'm still going through that point. And then 1/2, 1/4, and 1/8. So now my graph falls away to the right and rises when we go to the left. Okay? But once again, this graph is never going to touch the x-axis because all the powers of 1/2 are going to be positive numbers. Okay, and we call this kind of graph exponential decay. And again, I could draw some of the other graphs. If I change my base, if my base was 1/3, it's going to come up a little sharper here. If my original base was 10, when I flip it over, I have 1/10, and that's going to come up very sharply, and so on. Pause the video now and work on checkpoint 2. In this example, we're going to compare and contrast some exponential functions that are similar and see what changes are made in the graph when we change the exponent. Okay, so we're going to start with two functions, f of x equals 2 to the x power, and g of x equals 1/2 to the x power. Okay, we've already looked at both of these functions, but let's put them on the same graph. So this one is going to start at 1/8, 1/4, 1/2, 1, 2, 4, and 8. Now let's draw that in. And then I'll do the second one in orange. And you might remember that that one started at +8, 4, 2, 1, 1/2, 1/4, 1/8. So these two curves with reciprocal bases end up being mirror images of one another. Let's look at some other functions. What happens if I have f of x equals 3 to the 1 minus x, and g of x equals 3 to the negative x. Okay, I'm going to do 3 to the negative x first, since we've already looked at that one, or something very similar. So let's do x and f of x. So again, this is going to be 27, 9, 3, 1, 1/3, 1/9 and 1/27. So we're going to have to start at this point. So -2, 9, -1, 3, and so forth. What happens when I do this, when I have 1 minus x? You can make another table of values. I'll call this one g of x. No, we're going to call it f of x. And again, so you can see here the negative x is still there, but I've added 1 to it. What does adding 1 to the exponent do? Well, let's look first at just this 0 point here. Okay, if x is 0, this is just 3 to the 1, so it's a 3. If x is positive 1, I got 3 to the 0, so that's a 1. X minus 2 would give me -1, so this would be 1/3, and then 1/9. And up here I'd have 9 and 27, and then 1 minus -3 would give me 81. So graphing the things that we're able to graph, we'd have to start at -1 and 9, 0 and 3, 1 and 1, 2 and 1/3, and then 1/9 and 1/27. Okay, so I get the same graph, but it's been shifted 1 unit to the right. So when I add 1, I'm going to shift it 1 unit to the right. And this is the first graph we've had where the y-intercept is not at 1, it's at 3. Okay, let's look at 2 more functions. Look at f of x equal 2 to the 0.6x, and g of x is just going to be kind of our standard exponential function, 2 to the x power. We've done this one a couple times already, so I'm not going to do a table for it. We'll just go ahead and graph it and put my y-axis back in there. So we're going to start at 1/8, 1/4, 1/2, 1, 2, 4, and 8. So that's kind of our standard exponential function. What happens when I put this 0.6 here? I'm going to make an extra column here for 0.6x, and then we'll do f of x. -3, -2. When I multiply these by 0.6, you get -1.8, -1.2, -0.6, 0, and then positive 0.6, positive 1.2, 1.2, and positive 1.8. Okay, without a calculator, this is going to be pretty tough to come up with these powers, but there's a couple we know, or one. We know this is going to be 2 to the 0 power will be 1. So we still have this point. In general, the points are going to be pretty similar over here. But when we get to this side, the curve is still going to increase, but it's going to increase more slowly, as if we had a smaller number than 2. Okay, so these are the two graphs if I have x and some fraction of x. Now notice it's not the same as if I change the base to be a fraction. That makes the whole thing flip over. But if I change the exponent to be a fraction of x, I still get an increasing graph, but it just increases more slowly. Pause the video now and work on checkpoint 4. What would happen to our graph if we chose a nonlinear expression for the exponent? Let's look at what we get when we have f of x equals 2 to the negative x squared. Once again, table of values. This time I'm going to start with negative 2 and go up by halves instead of by whole units. Okay, when I do that, for negative 2, if I square that, I get positive 4, but then that makes it negative again, so this is 1/16 because I have to flip it over. On the next one, it comes out approximately 0.21, 1/2, 0.84, still at 1, and then 0.84 again, 1/2 again, 0.21, and 1/16. So I'm going to start my graph where x equals 0, and we'll just call this 1, positive 1. And then as I go out from positive 1, I can see that there's some symmetry. So 0.84 on either side might be about there. And then 1/2 we could maybe make about here. 0.21 about here. And 1/16 down here. So now I have a graph that looks very different from the traditional exponential graph. It looks almost like a parabola with that x squared exponent. Before we go on, I want to talk for just a minute about the number e. Okay? Some of you may remember the number e from high school, and some of you maybe don't remember that. Basically, the number e is very similar to the number pi. They're both irrational numbers, which means that they go on forever, but never repeat in a pattern. And the value for e is 2.718 2818 28459, and so on. Okay, I would not expect you to remember any more than this for the number e. That's a good approximation. You should have an e on your calculator. When we're working with e, I would suggest that you become very familiar with how e works on your calculator. Okay, in most scientific calculators, which is probably also the ones on your phones, you push the number first, or enter the number first that you want, and then the e to the x key. Okay, if you're using a calculator that's patterned more like a graphing calculator, you push e to the x first, and then the number that you want for x. So just make sure that you are familiar with your calculator and how this button is used on your calculator. This graph shows you three functions, 3 to the x, 2 to the x in red, and e to the x in between them. And it comes out, I think, like you should expect it. E at 2.71 is much closer to 3 than it is to 2. And so we see the graph of e to the x is also closer to the graph of 3 to the x than it is to 2 to the x. Pause the video now and work on checkpoint 6. In our last two examples for this section, we'll be looking at some real-world situations that can be modeled using exponential functions. The first one has to do with wine consumption. It says the annual amount of wine in millions of gallons consumed in the United States can be approximated by this function. F of x is equal to 34 e to the 0.029 x. And x equals 50 corresponds to the year 1950. So my first question is, how much wine in 1990? Well, if x equals 50 gives us 1950, then x equals 90 will give us 1990. So all I have to do now is substitute that in my equation. 34 e 0.029 times 90 gives me 462 million gallons. And then they ask, How about the year 2015? Well, we have to think a little bit more there. If 1950 is 50, 2015 would be 115. So 0.029 times 115. And that gives us a value of 955 million gallons. Okay, so you can see that the rate of consumption is going up very quickly. When you're working these problems with a calculator, I would suggest that you figure the exponent first. It can be difficult to put in multiplication in the place for that exponent. Easy to make a mistake. So figure out the exponent first, and then go back and do 34 times e to the power that you got. So pause the video now and work on checkpoint 7. Here's another practical application. The assets in billions of dollars for the multinational insurance company AIG can be approximated by this function. A of x equals 1756 e to the negative 0.91, negative 0.091 x. So right off the bat, looking at this, I got a negative exponent, which tells me that the value of these assets is going to be falling instead of rising. So what were the approximate assets of AIG in the year 2007? And they tell me that x equals 7 does correspond to the year 2007. So I'm going to get a of 7 equals 1756 e to the negative 0.091 times 7. So this gives me a total of $928 billion. Your book says 928.7. And now we want to know, what were the assets in the year 2015? So now we'll find A of 15 times 15, and this gives us a total of 448.4 billion dollars. So you can see indeed that this dropped in 2015 to less than half of this. So in those 8 years, dropped quite sharply. And of course, we know that in 2008 is where they lost most of that money, but it continued to drop after that. Okay, you're ready now to work on your homework assignment.